Okay, so hello everyone. So it's our great honor today to have Dr. Geng Chen, who will present his recent cutting-edge research on diffusion MRI and geometric deep learning. So his talk today will be on graph representation of diffusion MRI data and beyond. So let me just briefly introduce Dr. Geng Chen to you guys. So he is currently a research scientist at the Inception Institute of Artificial Intelligence in the UIAI. He got his PhD degree from Northwestern Polytechnical University in China in 2016. And he was a postdoc research associate at the University of North Carolina at Chapel Hill. And that's where we actually met. We were part of the IDEA lab directed by Professor Dr Geng Chen. His research interests include medical image analysis, diffusion MRI, a lot of diffusion, I would say, machine learning, and neuroscience. He published more than 45 papers in peer-reviewed international conference proceedings and journals, including MICAI, IIAI TMI, Neuroimage, and Medical Image Analysis, among other journals. He's also a reviewer for top-tier journals and conferences, such as Medical Image Analysis, also TMI, TIP, MICAI, IPMI, CVPR, ICCV, IIAI, IIAI, etc. So you guys can see a lot of cool stuff going on here. And today, his talk will be on graph representation of diffusion MRI data and beyond. So let's all welcome Dr. Chen to the BASIRA Eye for Healthcare seminars. And I will leave it up to you so you can share your screen and start your presentation. Thank you for joining us today. It's a great honor to have you here.
Okay, thank you. Thank Professor Rekik for the introduction. So now let me share my slide. Okay, one moment, please. Okay, so now I will start. So, okay, so today I'm very glad to present our recent work on diffusion MRI. So the title of the presentation is Graph Representation of Diffusion MRI Data and Beyond. I'm Geng Chen, a research scientist from Inception Institute of Artificial Intelligence. So this is the outline of this presentation. So basically there are 6 parts. First, I would like to introduce the background of this work regarding diffusion MRI and how to use diffusion MRI to study white matter. And then I will introduce the core idea of this work, the graph representation of diffusion MRI data. And based on this core idea, I would like to introduce 4 works. The first is diffusion MRI denoising via graph framelet matching. The second one is joint execute space superlution of diffusion MRI data. The third one is white matter microstructure transmission via graph neural networks. And last one is diffusion MRI reconstruction via graph adversarial learning. Okay, so first I would like to introduce some background. We all know that the human brain is a very complex system. In general, the human brain consists of 2 kinds of tissues. The first is gray matter. Gray matter consists of neurons and act like CPUs to process the information. And another one is the white matter. White matter consists of neural fibers, which act like a network to do information transmission between the neurons. So currently, the only non-investigative way to study the brain white matter is called diffusion MRI. It is a kind of MR technique. Using diffusion MRI, we are able to acquire the diffusion MRI data. And after post-processing, we can have 2 kind of very important quantities. The first is microstructure index. So as shown here, this usually based on the Diffusion MRI data, we can have the called microstructure index maps. And this kind of map is more like a 3D scalar maps. And different microstructure index represent different physical characteristics of the white matter. And the doctors can use this microstructure index to diagnose some brain disorders related to white matter. And also it is widely used in the neuroscience study. And the second one is we can use an algorithm called stratigraphy to reconstruct the whole brain tracks, which represent the 3D geometry structures of the brain white matter. So this stratigraphy result can be used for some like surgical planning and some neuroscience research. And furthermore, we can, based on the stratigraphy result, we can construct the brain connector. This is how to use the stratigraphy result to have the corresponding construct the corresponding brain connector. So basically, we have a stratigraphy result, and we also have the brain parcellation result. And then we can compute region-to-region connectivity to, and furthermore, we can, after we computing the every region-to-region connectivity, we can have the corresponding connectivity matrix. This is what's so-called structure connectivity, widely used in the research. And furthermore, we can have the brain connector. Okay, then I will introduce some details about Diffusion MRI and the challenges associated with Diffusion MRI processing and analysis. So for Diffusion MRI, there is a unicorn concept. Okay, let me find the. Okay, it's okay. So for Diffusion MRI, there is a unicorn concept called Q space. So Q space is more like a 3D space, and it is a 3D polar system. We can have different sampling patterns for Q space. And for example, the Cartesian sampling, which is widely used in the diffusion spectral imaging. Single shell spherical sampling, which is used in the clinical setting. And also its multi-shell extension, the multi-shell spherical sampling, which is used a lot in the research side. And so basically, given a point in Q space, we can define a Weaver vector. So based on this Weaver vector, we can define a corresponding grounding pulse. And this pulse can be used to design an imaging particle. So this particle can be used with a scanner to acquire a corresponding 3D diffusion-weighted images. So in this example, there are totally 515 points in Q space. So we have the corresponding 515 3D diffusion-weighted image. The one without diffusion weighting is called BASIRA image. So if we view the 3D spatial space as X space, and then we can see that actually Diffusion MRI data is defined in a joint XQ space, which is a 3D high-dimensional space. So this is a major challenge for processing and analysis Diffusion MRI data. How to resolve this problem? The answer is graph. So because graph is perhaps the most general data structure, and it is an effective tool to represent the high-dimensional data. Motivated by this, we propose to represent Diffusion MRI data as graphs, so that we can process and analyze Diffusion MRI data with traditional spectral graph theory and deep learning models, graph neural networks. So this is a pipeline for this procedure. So basically, we have a set of diffusion-weighted images, and we are able to construct the affinity matrix for represent or encode the geometry structure of the IQ space. And then the Diffusion MRI data can be represented as a graph structure data. So finally, we are able to process and analyze Diffusion MRI data using the tools that are designed for graph structure data. How to construct the graphs? Here we show example. So here xi and q chi as a represent the x space location and q space Weaver vector. So based on we are able to define a point in xq space. And we can also define another point, which is determined by xg and qi. So we are able to compute the affinity weight between these two sampling points using this equation. So basically, this is a combination of three Gaussian kernels. The first one is for the x space spatial difference. And second one is for the angular difference. Here, q hat chi is the normalized q vector. It is representing the grounding direction. And the last one is for the b-value difference. So here this is a definition of the b-value. It represent actually the lines of this q vector. So we can see that using this equation, a large weight, finite weight is assigned to two x space points that share similar grounding direction, similar b-value, and a similar spatial location. So after computing paired node in XQ space, after computing the affinity weight for paired node in XQ space, we are able to construct an affinity matrix so that the graph date can be represented as a function defined on this graph. So based on this core idea, we did a lot of research. In the traditional area, we propose denoising and super-illusion algorithms. In the deep learning area, we propose the microstructure estimation model and the reconstruction model. Then I will detail in each work. So the first work is for denoising. Denoising is a very important task in diffusion MRI. Because diffusion MRI suffers from low SNR, especially when the diffusion weighting is high. So like showing this example, the left one is the BASIRA image. And actually BASIRA image is equivalent to T2 weighted MRI image. You can see that a clear structure can be observed in the image and the signal to noise ratio is high. But for the diffusion weighted image, especially when the b-value is high, so this is the diffusion weighted image acquired using b-value of 3000. You can see that the signal to noise ratio is low and the structure cannot be clearly observed in the image. So the heavy noise restricts the quantitative analysis regarding diffusion MR data and reduces the reliable of subsequent analysis. An effective algorithm to remove the noise is called a non-local means algorithm. Non-local mean algorithm employ neighborhood matching to gather self-similar information and then perform weighted average to remove the noise. Like showing this example, here the red block B is the target block. And we have a set of query blocks, B1, B2, and B3. And we can see that actually B1 and B2 is similar to B, but B3 is dissimilar to the target block. So basically using neighborhood matching, we are able to compute the similarity weight for each block. And then we can use the obtain the similarity weight and the corresponding pixel values at the center block, at the center of each query block. And then we can remove the loss in a weighted average framework. So the idea is basically, so if we it's more like a repeated acceleration. So basically, if one image is the SNR is low, so usually in the acceleration stage, we prefer to acquire multiple images for one same skin, and then we do average so that noise can be removed. Non-local means is inspired by this this concept. So non-local means an effective algorithm to remove the noise. But it is designed for the 2D or 3D grid structured images. But as mentioned in the background, we know that diffusion MRI data is defined in a joint SQ space, which is a 6D head dimension space. So we are not able to directly use numerical means to remove the noise for diffusion MRI data. To address this challenge, we propose to remove the noise in diffusion MRI data using graph framelet matching. So the key idea is that we are able to represent the high dimensional diffusion MRI data as graph, and then we are able to do neighborhood matching on the graph, so that we can, for each node on the graph, we are able to gather its corresponding similar information, and then we can do remove the noise in a weighted average framework. Our proposed method consists of 4 major steps. First is graph representation. We represent the diffusion MRI data as a graph, and then we use graph framelet transform to extract the feature vector for each node on the graph. This feature vector encodes the neighborhood information of each node on the graph. And then we are able to use the feature vector to do neighborhood matching, so that we are able to gather the similar information in SQ space. And we are able to build the signal correspondence also in the high dimensional 6D space. After using neighborhood matching, we are able to compute the similarity weight for 2 sampling points in SQ space. So then we are able to remove the noise in a weighted average framework. The contribution of this work lies threefold. So first, it is a new neighborhood matching technique to overcome the limitations of traditional methods, which are unable to make full use of SQ space information. And it is also the first work that removes the noise in diffusion MRI data with graph representation and spectral graph theory. And in this work, we also dedicated to resolving important problems in diffusion MRI, providing significant value in a clinical setting. This is the data set we used in our evaluation. We used 2 sets of data set. First is synthetic data. Synthetic is based on the SB challenge phantom, and we simulated the data using the consistent parameters with the real data. And different noise settings are considered. We add a non-central high noise with different noise levels and different number of channels to the noise-free data to simulate different noise settings. The real data is acquired using a Siemens scanner. There are 3 shares, 144 grounding directions, and the image matrix is 140 times 140. Voxel size is 1.5 isotrophic. T and TR are shown here. So first, I would like to show some visual results for the neighborhood matching weight. I use 2 sets of experiments I use 2 sets of I would like to show 2 sets of results here. So first is based on the synthetic data. The top row is fiber ODF. Fiber ODF is more like a 3D function to represent the fiber orientation. Like this one, the fiber orientation is vertical. This one, it changes slightly. And for this one, it is a crossing fiber. The bottom row shows the corresponding signal profiles. And with colors represent the matching weight. Here, warm color represents a large matching weight, and cold color represents the lower weight. We perform experiment by selecting a point here, and then we do neighborhood matching with all other points on the sphere, and also its neighboring single sphere. And we can see that the matching is accurate. You see here, so correct information, similar information are localized by using our neighborhood matching technique. Another set of experiments is based on the real data. And here we choose 2 regions of interest to show the result. Similarly, we select a point here and then do neighborhood matching with all the signals in this ROI. And we can see that the matching is accurate and correct information are localized by using our method. So consistent result is observed in the sagittal view. This is the result for the this is a quantitative result evaluated using PSNR. We consider different noise settings, include a different number of channels, 1, 8, 4, 12, and different noise levels. And here we consider different baseline methods. Okay, so basically we can see that our method outperform all the state-of-the-art method in different under different noise settings. And in particular, when the single channel non-central noise with a noise level of 9% is added to the is adopted, our method outperforms the second best method by a large margin of around 2.8 dB. This is a result, visual result for diffusion weighted images based on the synthetic data. And our method is shown here, showing the bottom right. And the noise-free image is shown at the top right. So this one is a noise image. We can see that after using our method to do the denoising, the image quality is significantly removed, and the obtained diffusion weighted image is close to the ground truth. And also that for the baseline methods, we avoid the over smooth effect in the baseline method, and also effectively removes the noise, unlike the second best method, which is unable to fully remove the noise. This is diffusion weighted images for the real data. The close-up views are showing the bottom. So we can see that this is a noise image. So basically using our methods, the image quality is significantly improved, and also clear structure can be observed in the denoised image. Okay, so then we come to the second work. This is also a traditional method. This method is for diffusion MRI superposition. The motivation of this work is also to receive a major drawback of diffusion MRI. So here I show an example to explain this. So this is 2 images acquired in a clinical setting. The left one is a T1 weighted MR image. And usually in clinical, the resolution can be 1 millimeter isotropic. And the left one is a diffusion weighted image acquired from the same subject. And the resolution is 2 millimeter isotropic. So basically, we can see that the resolution of diffusion weighted image is much lower than that of T1 image. And the low resolution issue could introduce third partial value effect, which also reduces the reliability of subsequent analysis. And another drawback is the low resolution in Q space. In a clinical setting, because of limited acquisition time, where we can only acquire like 30 directions per share. So, but for the usually in the research side, we have plenty of time for the data acquisition. Sometimes we can acquire 90 directions. So this kind of high quality data allows the use of some advanced diffusion models, which can provide realistic characteristics for the white matter, but because of the low angular resolution Q space, this model cannot be used for the clinical setting. Yeah, so basically, diffusion MRI suffers from both low resolution in both X space and Q space. So to resolve this issue, we propose the XQSR, XQ space resolution. Um, we we achieve this goal by using an object function shown here. It is a recognition framework. We have a date for dim term, and we have another regulation term. So here, DHR is a high resolution diffusion date. O is in operation to map the high resolution data to low resolution one. And the DLR is the low resolution diffusion date. WIKGL is the XQ space neighborhood matching weight. We obtained using the graph framelet matching, the work we described in the last section. And P is an operation to extract a diffusion signal from the high resolution date. So here, date for dim term is used to preserve the original information during the supersolution. And recognition term encourages each signal to be represented as a matching signal in its search volume. HR to LR operation is a mixture of SQ space downsampling operation and X space blurring operation. To solve this equation, we first compute the deviation and equals it to 0. And after simplification, we have this equation. This is a large system, a linear equation. The definition of Z and W are shown here. Due to the limitation time limitation of the presentation, I will not go into the detail of the mathematical part. So for this large linear equation, so we solved it effectively by using a conjugate gradient method. So the conclusion of this work lies threefold. So first, we aim to resolve a critical problem in the clinical practice of diffusion MRI with non-local recognition and graph framelet matching. We jointly enhance the SQ space resolution of diffusion MRI data in a unified framework. And in this work, we make full use of SQ space signal correlation during the resolution enhancement of diffusion MRI data. This is the data we use in our evaluation. The synthetic is also the SB 2013 Hardy Challenge Phantom. And we simulate the synthetic data using consistent imaging parameters with real data. We consider 3 levels of noise, SNR equals 10, 20, and 30. For the real data, it is from the human connecting project. There are 3 shares. The low resolution for the low resolution data, the spatial resolution is 1.25 millimeters astrophic, and there are 90 gradient direction per share. And for the low resolution data, it is 2.5 millimeter, and there are 45 gradient directions. And the following are some imaging particles. Okay, so this is the PSNR results. It can be observed for different SNR. Our method consistently provides the best performance. And in particularly, it outperformed the second best method by a large margin of about 3 dB when the SNR equals 30. This is a result for the diffusion images. The left one is a high resolution image. Our result is showing the bottom right. And here is a low resolution image. So we can see that the image quality is significantly improved by using our method. And especially in this close-up view, you can see that clear structure is recovered, and the result is close to ground truth. In contrast, the baseline method all bring over smooth effect to the result. This is a result for the fractional anisotropy image, FA image. FA image is an important microstructure index map widely used in the clinical setting. The F image is shown here, and we show the corresponding absolute difference map at bottom. We compute the absolute difference map using the each reconstruct F image and the high resolution one. So lower absolute different value indicates the result is closer to the ground truth. So we can see our method significantly reduces the absolute different value and provide indicating, implying that the result, the corresponding F image is close to the ground truth. This is the result for the diffusion weighted images from the real data, and from this, from these three ROI regions, we can see consistent improvement. Okay, so this is result for the FA image for the real data. Yeah, so we can say our method reduces the prediction error. And the compared with the low resolution FA image, we can see that the image quality is significantly improved. Okay, so then we come to the deep learning area. So this is our third work on microstructure estimation. As mentioned before, so microstructure index are very important for the clinical setting, and in particularly some recently proposed advanced diffusion microstructure models. They are able to provide a rich characterizations of brain white matter structures, which will eventually give a large number of vital biomarkers for the diagnosis of brain disorders. Here I show two examples for the microstructure models. First is noding, and these are the corresponding microstructure index maps given by the noding model. And another is the model is DKI. And both noding and DKI, they require diffusion MRI data densely sampled in Q space. That means we need to acquire for the fitting of these models, we need to acquire multi-share diffusion MRI data with a sufficiently angular resolution. However, for the clinical data, usually it is acquired using a single share spherical sampling with sparsely sampled Q space. But for the expected data used for fitting these advanced microstructure models, it is usually multi-share, and the angular resolution is higher than the clinical data. So there is a large data quality gap between the clinical data and the data what we expected. To resolve this issue, deep learning has been employed for the microstructure estimation. The core idea of this deep learning models is to learn the relationship between sparsely sampled Q-space data and high-quality microstructure index estimated from densely sampled Q-space data. There are two major advantages. First, it avoids the requirement of diffusion MRI data with densely sampled Q-space. And also it is high computational efficiency, avoiding the time-consuming model fitting. A major limitation for existing method is that they usually overlook the Q-space data structure and the signal correlation between angular neighbors. For example, a widely used method is the multi-layer perception. Basically, the multi-layer perception (MLP), they view the input diffusion MRI signal as a vector without considering the data structure. This is a major problem for the existing method. So to resolve this method, we propose to represent a Q-space using a graph, which encodes the geometry structure of Q-space sampling point. And we are able to estimate the T3 microstructure from undersampled diffusion data via graph convolution neural networks. So this is an illustration for the whole framework. So basically for the clinical side, the accreditation is sometimes limited to about 6 minutes. And for the research side, so it is okay to acquire diffusion MRI data with about 1 hour. So we represent the clinical data using a graph, and we reconstruct the corresponding high-quality microstructure index from the research data. And we use graph convolutional neural networks to learn the mapping the mapping function between the graph structure data and the corresponding microstructure index. So this framework considers the Q-space data structure and harnesses information from angular neighbors to improve the estimation accuracy of tissue microstructure. Here are some implementation details. We use the fast localized spectral filtering for effective graph convolution. And residual learning is introduced into its training. Our network is trained to predict the node index. Here is illustration for the network. So basically, there are two radial convolution blocks followed by fully connected layers, and the final output is the expected microstructure index. The dataset we used in our work is diffusion MRI data from Baby Connecting project, and the data are acquired using a Siemens scanner. The resolution is 1.5 isotropic. There are 6 shares with 144 gradient directions. For the preprocessing, we first computed the node index from completed diffusion MRI data of all training subjects as prediction targets. And we subsample the diffusion MRI data uniformly in Q-space with different factors, including 2, 3, and 4. These factors corresponding 72 diffusion weighted images, 48 diffusion weighted images, and 36 diffusion weighted images. For each subject, we randomly selected 20,000 voxels from the brain region to form a training dataset with a total of 100,000 training samples. This is a result for the PSNR. So here we have two baseline methods, Amico and MLP. Amico is a traditional method. MLP is a widely used deep learning method. We consider different undersampling ratios. For the node model, it has 3 important index. The first is intracellular volume fraction, ICVF. The second one is isotropic volume fraction, ISOVF. And the third one is orientation dispersion index, ODI. Here all represent the combination of them. So we can see in different settings, our method consistently provides best performance. In particularly when for the ICVF index, when there are 36 diffusion weighted images, our method outperforms the second best method by a large margin of around 2.3 dB. Yeah, so this is vivo results for the intracellular value fraction. And this is the result based on subsampling factor of 2. And the top row shows the intracellular value fraction maps given by different method. Ground truth is shown in the left. And the bottom row shows the corresponding error maps. We can see our method reduces the prediction error, indicating the prediction result is close to the ground truth. This is the result for the subsampling factor of 3. Consistent improvement can be observed in this set of results. This is the result for subsampling factor of 4. And we can see that our method significantly reduces the prediction error, indicating that the obtained microstructure index map is close to the ground truth. Okay, Okay, so then we come to the last work for diffusion MRI reconstruction. This is also a deep learning work. For diffusion MRI, we know that it is a powerful tool to study brain white matter involved, and it suffers from long occlusion time, low SNR, and third partial value effect. So this is a table from the HCP 3T imaging protocol. We have compared with the commonly used T1 and T2 weighted MR image. First, the resolution of the MR is low, and also the occlusion time is much longer than that of T1 and T2. So in this project, we aim to reduce the occlusion time while preserving the spatial resolution. To achieve this goal, we proposed a new diffusion MR imaging protocol called SITE. This is a conventional encoding. This is the centralized Q space. Each point is corresponding to a diffusion weighted image. Here, all the diffusion weighted images are fully sampled. To reduce occlusion time, we only acquire a subset of the diffusion weighted image. And here we can see that for the proposed imaging protocol, for each diffusion weighted image, only a subset of slices are acquired. And for different diffusion weighted images, the subsampling pattern are different. So this is to ensure that there are enough complementary information among the diffusion weighted image, so that in the post-processing stage, we are able to recover the missing slices by using the complementary information from other diffusion weighted volume. Okay, so using SAT, we are able to acquire a set of sliced undersampled data, and then we need to recover the fully sampled data from this undersampled data. So basically, we achieve this goal by using graph adversarial learning. So we aim to predict high quality fully sampled diffusion data from sliced undersampled data acquired using SAT. So first we do graph representation of sliced undersampled diffusion data, and then we formulate the high quality diffusion data prediction as a high dimensional image synthesis problem, which is received with graph neural networks. And our framework is able to exploit to the relationships of neighboring points in SQ space by using a graph. There are a number of novel features in the proposed model. First is adversarial learning, and also the graph neural net, microstructure laws, and others. So this is the main framework adopted in the proposed model. So basically, we have a generator, we have a generator and a discriminator. So the generator accepts the input undersampled data to predict the corresponding fully sampled data. And the discriminator is used to distinguish whether it is synthetic data or it is ground truth data. We enter relatively to optimize generator and discriminator to make sure the final prediction can fool the discriminator, so that we are able to generate a realistic prediction of high quality fully sampled diffusion data. This is the network architecture for the generator. We have three parallel branches for different views. So for each, here we use different graph convolution neural networks to predict the corresponding fully sampled data in this view. And then at the second stage, we merge the predictions from the last stage, and then using another graph convolution neural networks to generate the final diffusion weighted values by considering the correlation across the scan directions. This is the network architecture of the graph neural network for each view. It is a multi-scale relative graph neural net with pixel shuffle. So basically, we have a multi-scale input to enrich the input information also introduce residual learning to its training. And finally, because this is more like a super resolution work, so we have like a multi-channel feature maps here. We do a pixel shuffling for the final prediction, final height dimension prediction. And also, we introduce a microstructure loss here. So the basic idea is to ensure the predicted diffusion MRI data could have good diffusion microstructure properties. This is data used in our evaluation, and we use the data from HCP. The voxel size is 1.25. We perform four-fold cross-validation with 16 subjects. Under sampling factors 3, 4, and 5. After being divided into 3 subsets for each scan direction, each subset was divided into R groups. And also each diffusion-weighted image is normalized by the BASIRA image. This is quantitative results evaluated using different metrics, including mean absolute error, peak signal to noise ratio, and the structure similarity index. And the top part is for the result regarding diffusion weighted image. We can see the proposed method outperforms the baseline methods at different undersampling ratios. And the bottom shows the result for the generalized FA, which is another microstructure index. Consistent improvement can be observed in the GFA result. This is the vivo results regarding GFA maps when the undersampling factor is 4. The ground truth is shown at in the right, and the proposed method is shown in the third column, and the other 2 columns shows the baseline methods, and the bottom row shows the error maps. And we can see that for the region marked by the error, our method provides a result that is close to the ground truth. And also from the error maps, our method is able to provide reduces the prediction errors, indicating the GF maps given by our method is close to ground truth. Similar improvement can be observed in other views. This is result for the coronal view. And also this is result for the sagittal view. This is result for the fiber ODF. The ground truth result is shown in the left. And you can see, especially in this local ROI region, we can see that our method provides a result that is very close to ground truth. In contrast, the baseline method provides an unsatisfactory result in these regions, and results are dissimilar to the ground truth. Okay, so I would like to also introduce other works that are finished by our group. So the first is the COVID-19 CT imaging study. We propose a non-infection model called InfoNet. This work is published in dMRI and last year, and the current citation is over 200. It is a highly cited paper and also the second most cited paper in Google Scholar under keyword COVID-19 infection citation. And also I participated in the Baby Connecting project and help to develop the imaging protocol. The paper is published in your image. Current citation is over 100. It's also a highly cited paper. And this work has been cited by some papers published in PNAS, Nature Machine Intelligence, Nature Communication, and also have some collaboration project regarding image synthesis, diffusion model, phase correction, multi-site harmonization, superillusion, brain atlas, brain development. If you have some interested for these works, please visit my homepage, for example, Google Scholar or ResearchGate. Okay, Conclusion. So first, high-dimensional data representation is a major challenge in processing and analysis diffusion MRI data. And graph is a general data structure showing superior abilities in the representation of diffusion MRI data. By represent diffusion MRI data as graphs, we are able to develop traditional methods for effective noise reduction and superillusion of diffusion MRI data. In addition, we also propose the powerful GNN-based models for the microstructure estimation and diffusion MRI reconstruction. Finally, I would like to thank UNC at their lab where I finished my postdoc training, and also the IIAI Medical Image Analysis Group, where currently I'm working as a research scientist, and also the support from NIH grants. Thank you for your listening. Yeah, please let me know if you have any
Thank
questions.
you very much. That was a great presentation and lots of interesting works. I'm sure you covered 4 topics, but you had way more to cover. However, we have lots of questions for today. So I've noted a few questions. We have one from the audience. So let me start with the audience, and then I'm going to move forward with the other questions. So I've always loved the images of diffusion, you know, like ODFs, the colorfulness, the beauty of the diffusion MRI. It's so mesmerizing. But what really entices me throughout your presentation is, like, you know, how the new field of geometric deep learning and graph neural networks is now also invading diffusion MRI and outperforming existing traditional methods, leading to excellent results, as you have shown in your recent works. So let's start with the first question. The first one is by Ahmed. He's asking, in your last presented work, you seem to input a graph to a graph neural network and then apply pixel shuffling. So basically, what are the nodes in the graph here? So he's asking, basically, when you input the graph to your neural network, do you input actually images, or do you input, for example, cubic patches? What are the exact inputs? Can you explain a bit more the input and the output of your neural network? Yeah, this slide, exactly, yeah.
Okay, yeah. Thank you for the question. So, yeah, so basically the input of the graph neural network is more like actually it is a patch. It is a so because you know, so for the whole diffusion weighted volume, so for the whole set of diffusion weighted volume, it is very large. So basically, we extract blocks from the diffusion weighted volumes to construct the corresponding graph and represent the blocks as a graph structure data, so that it is able to we are able to feed the graph structured diffusion MRI patches to the graph convolution neural networks for certain tasks. Yeah, here we input is actually extracted blocks from the diffusion MRI data.
Yeah. Okay, cool. So basically, like intensity images, like from the diffusion MRI. What is the value of each pixel in your image? It's like, you know, it's an intensity block, right? It's a 3D block, right? It's like a cube.
Actually, it is. I can say it is more like a 4D blocks.
A 4D block, yeah.
Yeah. So actually, for diffusion MRI, it is a little bit complex because, you know. Let me go back to the introduction part. So yeah, usually for diffusion MRI data, the data structure is always a very not very straightforward concept. So yeah, so actually here, so you can see that like these are like all diffusion weighted images. If you like do not consider Q space, you can directly view the stack of this diffusion weighted images as a 4D image, similar to function MR. actually, I know that some like researchers they process the diffusion MRI data as the 4D data, but the problem is that if you view the fourth dimension as a single dimension, and then you overlook the Q space information. So actually, yeah. So basically, what we fed to the network is patches, is a set of patches, but these patches are represented as a graph by considering both the Q space and X space.
Yeah, this is how you explained it earlier when you computed the affinity matrix. You take into account the location, which is the image in the 4D space, because you have different gradients, and then you have the gradient themselves, right? Like basically, and then you have the B, right? The B value. That's your formula that you use to compute the affinity matrix of your input graph, right?
Yes.
Okay, cool. So like many here are not very familiar with the Q space. So one simple question is from Alesh, is asking, is the Q space representing a manifold, a geometric space? Can you just, give the intuition or explain it in a simple way? What is this Q space? So most of us, all of us, I would say we're very familiar with images. So when we say, like functional MRI, 4D images, diffusion MRI, it is clear. But for the Q space, it's very particular to diffusion MRI. Can you explain it in a more intuitive way?
Yeah, sure. Yes, thank you for the question. So, okay. Q space. So, I think the shape or the sampling pattern in Q space is determined by which kind of sampling pattern you choose. I think you can see the slide, right? Okay, so basically for the Cartesian sampling, it is more like a grid structured sampling pattern. So you can view Q space as, I don't know, similar to the images because it is grid structured. So, but for this single shell spherical sampling, it is widely used in clinical setting. The date here is actually more like distributed on the sphere. So it is more like a sphere, structured data. So I would like to explain this a little bit more. So, okay, so for example, okay, so this is more like the diffusion image we acquired. So giving the same spatial location, given a specific spatial location xi, we can select a signal from different images, right? And these signals can map back to the Q space. Okay, so yeah, basically it is like the data is determined by two spaces. So you can have different representations of the data. For example, for my microstructure work, I just consider the Q space. I represent Q space as a graph. So actually my input for the deep learning model is this kind of like a sphere structured data. So basically, so if you stack this diffusion image together, it is more like a 4D image. And given a spatial location, you can extract a vector. Okay, so this vector, based on its corresponding gradient table, you can formulate this vector as a sphere structured data. And we further represent the data as a graph to use the graph convolution neural network to finish a certain task.
Right. Yes.
Yeah, I'm not sure if it's clear.
I think it's getting much clearer. So basically, it's a local representation that is spherical of your data, and then you have the other one is Cartesian. So these are two different representation of the same sample, I would say. But you combine both of them because they capture two different properties of your sample. That's like in a simple maybe way. Great. So we have another question from Mohammed. He's asking, In the last proposed method, how are the gradient vectors selected without redundancy of information?
Oh, okay. Yeah, this is a very good question. So let me go to that slide. Oh, here, right. So the question is that how to like select slices in each diffusion weighted volume. Uh, is my understanding correct? So basically,
Yes.
how to? Okay, okay,
Basically, the gradient
perfect.
vectors,
Yeah.
how do you select them in a way that you don't have a lot of
Mm.
redundancy? You have this complementarity between them.
Okay. So actually, there are two parameters controlling the selection of slices. The first parameter is like which direction you would like to select the slices. For example, I think so. For example, this one for this diffusion volume, the slice selection direction is more like a vertical. I think it should be like for this one, it is another direction. So this is the first parameter. And we can also say that for this one and this one, actually the slice selection direction are the same, but the final selected slices are different, right? Because you can say that this this is because another parameter is like an interval. So where you would like to start to select the slices, so that we like use these two parameters to control the slice selection in different diffusion weighted volume, so that the complementary information can be maximum among the diffusion weighted volumes. Yeah.
Okay, yeah, cool. Thank you. Thank you again. Now, another question. So Ahmed is asking, in your last two works, you have very few subjects, around 12. How are you avoiding overfitting when you are training your neural networks?
Yeah, this is also a very good question, and also some like real problems we are facing during the training of the model. So basically, for this microstructure work, we are actually using the voxel samples. So like just aforementioned, so it is more like spheres. So we use this voxel sample to do the training. So basically, even we have like a small number of subjects, but we have a lot of training samples in this case. And our evaluation, based on our evaluation, and also these samples are sufficient to training an effective model. And for this work is actually we are using like patches to do the training. Um, I think also that we have, because we are using patches to do the training, so that we can extract a lot of patches from the data. Some details, because this work is finished with the collaboration with Dr. Yomi Hong. I think for some details, I may need to like check the papers. I didn't remember exactly how many patches used in this work, but I think based on the experiments, these patches are sufficient to training the model.
Okay, yeah. So I think, yeah, you answered the question. So the way I understand it is that you perform patch-based training. So instead, it's not actually 5 samples that you're training on, it's hundreds,
exactly,
thousands of samples. And that's why in that way, you can try to avoid overfitting. So you have actually a large number of samples to train on, because you do patch-wise or sphere-wise, like depending on the location. Cool. So I do have a question. So in terms for the super resolution work, which I find very interesting, and like, you know, all of those are interesting, like clinically extremely relevant. You're trying to get microstructure images from low resolution images, and also you're trying to get high resolution diffusion MRI from low resolution one. So exactly, so we have this objective function. So the way, maybe you can clarify a little bit, what is exactly that you're trying to estimate or learn? Because in this example, I see that you have an operation that is you downsample. So basically you take a high resolution image. I would assume that's a training sample. You make its quality worse. So you downsample it into a low resolution image, right?
Yes.
And then you want to minimize the distance between the downsampled image and then the ground truth low resolution image. So if I just look at this formula, I would say what you're trying to do is to learn an operation or a mapping that simply deteriorates or worsens the quality of the image. However, as I can see here, the title is super resolution, right? So the idea is like, when you input to your algorithm, what you input to your algorithm is a low resolution image. And then what you get as output is a high quality image. So can you connect these two? Because so like, can you clarify a little bit how you're actually solving a reverse problem, I think, no?
Oh yeah, exactly. So
yeah,
it is this object function is for a reverse problem. So actually here dHR is the one we want to predict. So it is unknown. So we want to use this equation to recover dHR. So basically, usually for the date-for-date term, it's like to here dHR. Oh, sorry, DLR is more like the observation. So we can acquire. We have the low resolution data. We want to recover this high resolution data. So for the date-for-date term, O is an operation to map the high resolution to a low resolution one. So basically, this equation is encouraged during the in the representation, the low resolution image, low resolution information is well preserved in the high resolution data. So suppose we have a prediction HR, and we use this one we use O to map it to a low resolution one. And here we compute L2 norm here to make sure that the downsampled version of high resolution is as close as the low resolution one, so that the original information can be preserved.
All right, so I have just one question. So what about if you formalize things differently? So because we have a line of work on graph super resolution, on brain connectivity super resolution, but we work directly on the connectome. Basically, we work directly on the connectivity matrix of the brain. So one of the works that we've done at the lab here is that basically we use, for example, a graph GAN. You input a low resolution graph with a few nodes, and then you try to get a high resolution graph with many more nodes. And then the idea in the loss function, what we try to minimize is the distance between the output or the generated high resolution graph directly, and the ground truth one. So we don't do any downsampling, reverse downsampling.
Oh, I see.
What are the differences between these two different conceptualization or formalization of the super resolution concept? So one is basically just comparing the output in the ground truth directly in the high resolution space. The other one compares in the low resolution space, the original one, by downsampling the predicted high resolution data. So how do you see both? How do you compare or you think about both formalizations?
Okay, yeah. This is a very good question. So here, okay. So actually for this a realization framework, it is more like an unsupervised method. So there isn't any training. So this is a totally unsupervised method. So I know that for example, you training a deep learning model. So usually you have the training data, so that you have ground truth high resolution image, so that you can compute, for example, some representation loss to minimize the distance between the prediction and the ground truth. Here the situation is a little bit different because this is a totally unsupervised method. We don't know we don't know what is high resolution data, and
so that answers Thank you. That is
Yes. So we need to use it.
you're going fully unsupervised, which is much more challenging than having a ground truth data to compare against. Okay, cool. Thanks for clarifying. Now we have another question from Ala. She's asking, I see that the GCNN model was used to learn the graph representation. I would like to know why do not consider different graph convolution operations like the one proposed in GCN, graph convolutional network, or edge convolution operation? Why you are using graph CNN?
Oh, so the question is that, let me change the network. Oh yeah, so basically here why we use this fast localized spectral filtering instead of other graph convolutional.
It's like instead of exactly operations, for example, the graph convolutional, the GCN, the graph convolutional network, you operate directly on the graph. You don't consider any part of the learning process as an image. So you don't use like a typical CNN combined with a graph. So basically you operate on the graph directly.
Yeah.
Oh,
okay. Thank you for the question. So, yeah. So basically, yeah, I think it is a good idea to explore some potentials to combine the convolutional neural networks with graph convolutional neural networks, because actually for diffusion MRI, so although it is a high dimensional data, but after using some certain data representation method, it can still be viewed as images. Even although there is some loss of information, but it is still okay to use CNN to extract some informative features from the diffusion MRI data, and then we are able to combine it with the information provided by graph neural networks. I think, yeah. So actually, we have a work. I think that one is for super resolution. We propose a hybrid network. So basically, we first that is a collaboration project. But the basic idea is that we first use CNN to extract features, and then use convolutional use graph neural networks to further explore or to capture the Q-space correlation information, and using this both CNN and graph convolutional networks to get better results. Yeah, I think it's a good idea. Yeah.
Yeah, thank you. So basically, here you went for GCNN, but you can also combine both, because diffusion is originally an image, but then you represent it as a graph to capture the relationship between different parts of the image, but still you can use the typical, image-based convolution, and you combine it with a graph-based convolution. Then this hybrid model will explore both representations of the data and characteristics. Awesome. Okay, thank you. Now I do have a few questions. So for the when it comes to the super resolution work and all these works, reconstruction, denoising, so basically how do you see the generalization of your models, of your frameworks to tractography directly, working on tracks? Because I know tractography, when it comes to diffusion, you have there was a Mikai paper, I forgot in which year was published, maybe 2018 or so, where they compare different, diffusion tractography algorithms, and they found that there might be a lot of variation in the connectome the structural connectome that they are outputting at the end. So, so there was a lot of, how do I say, the field is amazing, but it's very challenging when it comes to the sensitivity of the tractography algorithm to the input hyperparameters of the model. But anyway, so what I'm talking about here, aside from that, like let's say you have a perfect tractography algorithm, you generate fiber tracts directly from a low resolution, a few gradients, as you said, maybe 30, and then you generate tracts from 90 gradients. And yeah, so how do you see the generalization of your models here, how you're formalizing all of these works to tracts directly? Yeah.
Yeah, this is a good question because tractography is usually a very, very important a target or output of the dMRI data. Yeah, so actually we have some results. I think it should be for the fiber ODFs in the paper. For this, both this, as you mentioned, for the superresolution work, we have some fiber ODF results showing the paper, and our result shows that so after using the superresolution, our superresolution algorithm, we can reconstruct high quality fiber ODFs. So basically, oh, 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 I think I have some. Oh, it's not here. Anyway, so our result shows that basically using the proposed the denoising method or superresolution algorithm, we can have better fiber ODFs. So basically, for the fiber ODFs, it is more like an input for the tractography algorithm. So usually for most tractography algorithm, we first predict the fiber ODF and then detect the fiber peaks. Fiber peaks is more like the local fiber direction. And based on this direction field, we are able to construct the tractography result. So that means better fiber ODF and better tractography. So basically, based on our evaluation, our method is able to improve the fiber ODF result. So that means the corresponding tractography result will be better. I remember for the denoising work in the paper, we have a set of result for some different fiber bundles, and basically using our method, we can reconstruct using our method to denoise a date, and based on denoise date, we can reconstruct rich fibers, more fibers, and also the fibers are clean. So this matches what we are expected for the tractography, and yeah, so basically it can improve the reliable of tractography results.
Cool. Thank you. Thank you. So basically, yeah, so you have already solved the problem, because once you have reconstructed data or super resolved the data, you can easily perform any tractography algorithm, apply it to the data, and then get the tracks in the high resolution space, for example, and in the denoise. Cool. Now, what are the challenges that you have faced when training neural networks on diffusion on the XQ space representation of the diffusion data, like in terms of hyperparameter tuning, in terms maybe a long time of training? So what are the real hands-on challenges to using graph neural networks and applying them to diffusion data?
Yeah, this is a good question. I think there are several challenges. So the first one should be the representation part. So basically, currently we for the last work reconstruction work, so we can only use the patches to train the model. So basically, there are two reasons. First is to avoid overfitting. Another is the limitation of the memory. So we can use relatively small patches to do the training, because so for the gradient for the dMRI data, like for the HCP, so there are totally 215 gradient directions in Q space. And suppose we use a patch with a radius of 5, and then the x-space points are 125. So basically we have 125 times 270. So my point is that that will be a very, very large graph. So that is a reason why we can only use a small graph to, small patch to train the model. So usually small patch is like, it is okay to, it has some advantages to avoid overfitting, but if you use relative small patch, and because sometimes I think it is, you don't have very sufficient X-space information. Yeah, I think this should be the major challenge to currently, the major challenge for us to like using graph convolution neural networks for the diffusion MRI.
Yeah, thank you. I think all of us have the same problem, actually. Like you're trying to circumvent the RM issues. The memory exploding by making the data smaller and prolonging the time of the training. Cool.
Yeah.
Okay, so maybe if we don't have more questions, I can have one last question. So where do you see the field of diffusion MRI, evolving with these new emerging graph neural networks, these generative learning models where you can generate anything from anything, you can input low resolution diffusion, get high resolution, you can have noisy image, get denoised image, you can have, low sample, low quality image, and you have like an upsampled image in a different way. You get microstructure from conventional diffusion. So there is a lot of things that you can do using diffusion data, but what are maybe the disadvantages of using or training such black box, models? Because at the end, what you're generating, you're trying to optimize this loss function, but how can you guarantee or know that what you're generating doesn't have any hallucinations, is very reliable, that the network is not making things up maybe a little bit? Also, like when you train a neural network, it is very constrained by the data that you're feeding to it. So how can you also guarantee the generalizability of your model or your neural network to maybe different samples? Maybe you might have diffusion MRI with some atypical structures. Okay, so how do you see the generalizability? How do you see the robustness or the reliability of your generative model, that you're not hallucinating? What do you think about these issues when it comes to generative learning and diffusion MRI?
Yeah. Yeah, so yeah, I think this is a very good question. I think for the whole image synthesis group, this is always a very important question, but sometimes kind of tough for the researchers in this field. So I think basically, so currently, I think for the image synthesis, it is okay to use the synthesize the image to do the to improve analysis for the okay, so it is okay to use the synthetic data to do some certain tasks. For example, for the missing data, and for example, for the restoration, if you have like a multi-model restoration problem. And my point is that it is okay to use the synthetic data to improve some subsequent algorithms or analysis. But there is, I think there is still a large gap between using the synthetic data for the diagnosis. I mean, the doctors directly use the synthetic data to do the diagnosis. I think that this one is still very challenging, but definitely we can use the synthetic data to improve the pipeline, to improve some subsequent algorithms. And also for the generalization, yeah, so for the deep learning model, generalization is also a tough problem. I think, but currently, so for some domain generation or domain adaptation. I think these are very good directions to improve the generation of the model. Um, yeah, yeah.
I cannot agree
Yes.
more. I mean, like, I can agree more. In terms of domain adaptation, I think that can solve a lot of issues when it comes to generalizability and multi-source data. And also, I know that these two are, how to say, like, you know, the holy grails of the deep learning field, particularly generative learning. How can we generalize? How can we make sure that, you know, what we're generating is biologically sound? And as you said, maybe we're not at the stage where doctors or clinicians can directly use the generated data, but I do believe that we are getting there. And the point is, like, you know, using diffusion, medical data, medical imaging, and all of that, hopefully we'll get, you know, without the need to acquire high resolution, costly data, we are able to use algorithms and leverage large scale data sets that are collected globally to generate you know, reliable images. Cool. I think we've come to the end of this seminar. Thank you so much for taking all of our questions and for your great talk. Let's all give a Zoom round of applause to Geng. So where is the emo? Like, here we go, like celebrating. And thank you so much for joining us today. And hopefully we'll get to meet in person again in one of those conferences soon. And yeah, thanks for taking part in our BASIRA AI for Healthcare seminar again.